This is the first part of our notes on optics. We'll cover some basics from chapter 22, but most of these topics are found in chapter 23. So a quick overview of waves. Periodic waves have some source that is continuously oscillating. If we look at some particles in the material itself, as the wave passes through, those particles oscillate back and forth about some equilibrium point, similar to what we saw with simple harmonic motion. And waves carry energy from one place to another. And there's two main types of waves. We have our transverse waves, as seen on the left, where the particles are oscillating perpendicular to the direction the wave moves. And there's compression waves or longitudinal waves shown on the right, where the particles oscillate parallel to the direction that the wave moves in. Some terminology review. Wavelength is the distance from one point on the wave to the next similar point, so from one crest to the next crest, for example. Amplitude is the distance of maximum displacement, so from the crest to our equilibrium position, or from the trough to the equilibrium position. The period is the time it takes to complete one cycle, and frequency is the number of cycles completed each second. Remember, period and frequency are just inverses of each other. So this is all about EM waves today. So electromagnetic waves, often shortened to just EM, are composed of these oscillations of electric fields and magnetic fields. We use capital B for magnetic, by the way. We'll talk way more about electric fields and magnetic fields when we get to electromagnetism second semester. For now, just know that they're electric and magnetic fields that are oscillating. It's not actually particles that are oscillating. So one real special thing about EM waves is they can travel through a vacuum. This is opposed to mechanical waves, which require a medium to travel through. EM waves are also transverse waves. So those oscillations of the E fields and B fields are perpendicular to the direction that the wave's moving in. All EM waves have a constant velocity when traveling through a vacuum, and that speed is 3 × 10⁸ meters per second. It's not exactly 3.00, by the way. That's rounded to 3 decimal places, or 3 sig figs. And it's the same speed if we're talking about EM waves traveling through air. It is a tiny bit slower in air, but it would still round to 3.00. A physicist by the name of Michelson carried out one of the most precise experiments measuring the speed of light in the early 1900s. He actually did this experiment in Southern California, and the basic setup is shown on the left. So we have a light source with light directed towards this rotating mirror. The light will reflect off of the surface of that mirror, and depending on the position of it as it's rotating, you may have some of the light moving off to the right toward a fixed mirror, very far away, by the way. This is not drawn to scale. It then reflects off the fixed mirror back to the rotating mirror and potentially toward an observer. So if this rotating mirror is rotating at the correct speed, then the observer detects the light. But if it's going any faster or slower, then you're not going to have this happen. So the observer would not detect it. So Michelson was able to get within about 1/1000th of a percent of the correct speed of light. So incredibly accurate and precise measurements. He was actually the first American to win a Nobel Prize in science for his experiments with optics. This is the electromagnetic spectrum. It's just a diagram showing you all the different electromagnetic waves and the names we've come up with for sort of different ranges of frequencies and wavelengths. So keep in mind, these are all EM waves. These names just describe where they're located or maybe how they're used. So don't think of them necessarily as different waves. So at the sort of bottom end in terms of frequency, we have our radio waves. So these are the lowest frequency but longest wavelength EM waves. Next, we have microwaves, which includes your cell phone. Above that, we have infrared. That means below red, which indicates its position on the EM spectrum. Because right above infrared, we have our visible light, our Roy G. Biv spectrum. Above visible, we have ultraviolet. That means above violet, which again makes sense. Then X-rays, and at the highest frequencies, we have gamma rays. So again, all of these are EM waves. They all have that same constant speed in a vacuum, that 3 × 10⁸ meters per second, which is written as a lowercase c. So our wave equation, V equals lambda f, becomes c equals lambda f, as long as it's in a vacuum or air. You should know, by the way, the relative positions of different waves in the spectrum. You don't need to memorize values, though it will be helpful to keep in mind the wavelengths of visible light, just sort of to check your answers. If you're solving a problem and you know it's some visible light, you should end up with wavelengths that are between 400 nanometers and 750 nanometers. Here we have our first example problem. You can pause and resume when you're ready. So for the AM radio waves, I'm using my wave equation with the velocity as c. And solving, we get 244 meters. For the FM radio waves, same process. And I can see that it's a smaller wavelength, which makes sense because the FM radio waves have a higher frequency. For the rest of this chapter, we'll be looking at these EM waves as rays rather than as a series of crests and troughs. So we're not going to be drawing, these sine curves. We'll start just drawing arrows to represent the direction that the light waves are traveling in. So over on the left in the diagram, we see this source of these waves. So it's this blue pulsating sphere, and it's emitting waves in all directions. So you can imagine the crests spreading out in these sort of spherical shells, and then troughs similarly spreading out in the same manner. We're looking at just a portion of those wave fronts. You can think of wave fronts as just crests. And if we are zooming out far enough, eventually those wave fronts appear to just be flat. So we have these plane wave fronts. And if we're using arrows to show the direction that these wavefronts are moving in, you can see that the arrows eventually appear as if they are parallel to each other. So we're going to start using these rays, these arrows, to represent the direction the waves are moving in. It doesn't tell you anything about the wave itself, just which way it's moving. So we're going to be talking a lot about mirrors, and so we'll need to remind ourselves of the law of reflection. So this tells us that the angle of incidence equals the angle of reflection. And remember that we measure these angles with respect to the normal line, which means the line that's perpendicular to our surface. There are two types of reflection. There's what's known as diffuse reflection, which occurs with rough surfaces, and specular reflection, which occurs with smooth surfaces. And when I say rough and smooth, it's not always something you can tell just by like rubbing your finger against the surface. It has to be microscopically smooth. So over on the left, we have an example of diffuse reflection. So you can see this could be paper, wood, rough water. Most objects exhibit diffuse reflection. And one way we can tell it's diffuse is if you imagine some source of light and you have these parallel rays coming in. So this could be some object that's far away, but even not, it works for any object really. But just imagine these parallel rays coming in. You can see that depending on where they hit the surface, they're going to reflect off kind of at different angles. And that's because the normal line at each point is kind of facing a different direction. So our reflected rays are no longer parallel. And what that means is you would see the object itself. You're not going to see the original source of this light. On the bottom right, we have an example of specular reflection. So this would be something like a mirror or calm water or polished metal, something very smooth, smooth at the microscopic level. So now our parallel rays coming in from our source reflect off, and they are still parallel to each other. So what that means is you're not going to actually see the object that it's reflecting off of. You're going to see the source. So keep in mind the main difference between diffuse and reflection is how the light reflects off the surface, and how you would tell is just by whether or not you see the object or if you see a reflection. All right, so when you're looking at paper, you see the paper. When you're looking at a mirror, you don't see the mirror, you see something else being reflected in the mirror. So with mirrors, the most common examples of mirrors are plane mirrors or flat mirrors. You have a normal line that's always pointing in the same direction. And down at the bottom, you can see on the left, we have one ray shown where it goes from the top of our chest piece here, our object, to the mirror and into the person's eye. Your eye doesn't know that the mirror has changed the direction of that light ray. So your eye would imagine that the light ray originally came from where that dashed darker black line is. So it looks like the line came from the far side of the mirror, behind the mirror. On the right, we're drawing in a second ray. And you can see that those two rays, they both start at that sort of top corner of the object, but they're spreading out, they're diverging. When they reflect off our mirror, they're still diverging. Your eyes would know that they came from the same point. So those two diverging rays, if you imagine where they came from, again, we're using these dashed lines behind the mirror, and you can see where those rays meet up, and that's where the image itself is located. So this is referred to as a virtual image because our image is located behind the mirror. There's not something actually physically there. And this is what we would call a ray diagram. So with plane mirrors, you always get the same type of image being produced with the following properties. So the image is always upright. It's always the same size as the object. It's always as far behind the mirror as the object is in front of it. And remember that being behind the mirror means that that image is virtual. And the image appears reversed from left to right to the observer. But keep in mind it's not actually reversed. So if we look at this picture, here we have someone raising their right hand. And you can imagine if that person turned around, so they were facing sort of us, their right hand would be on the other side of their body when they do a 180-degree turn. So here the image, it appears like the person in the image is raising their left hand. So you might think, all right, it's reversed. But the way I think of how it's not reversed is if you imagine someone like tying string from, his actual forehead to the image of his forehead on the mirror, and then from his hand, his raised hand, to the raised hand of the image, and from his shoe to the image of his shoe. So if you were to tape out all of these strings, none of the strings would cross each other, and that's what it means to not be reversed. All right, here we have an example with a ray diagram and a plane mirror. So we have this woman standing in front of the mirror, and the question is, what's the minimum height of the mirror needed for her to see her full reflection? So I'll let you see if you can figure it out, and then we'll discuss. So first, in this picture, we see that her total height as measured along the mirror is from point A to point D, and we can break that down as being equivalent to from A to C, which is at her eye level, plus C to D. If we're looking at the top figure, you can see a ray that comes from the top of her head, from point H, to the mirror and then into her eyes. That part of the mirror that would be needed is from C to P. So that from C to P, that part of the mirror allows her to see from her eyes and above to the top of her head. She doesn't need anything above point P. That would just allow her to see above her head. In the bottom figure, we're looking at a ray drawn from her feet to the mirror into her eyes, and we could see that the ray hits the mirror at point B. So the amount of mirror needed for her to see her feet is from C down to B, and that is halfway from C to A. So the total height needed would be C to P plus C to B, which is half of A to C and half of C to D, which is half of her height. So notice that this does not depend on how close or far away she is from the mirror. No matter what, she needs the mirror to be half of her height. It does have to be positioned at the correct height as well, so just to be clear. And probably the most common misconception is that the farther away you are from the mirror, the more of you you'll be able to see. That's not true, and it's good if you can actually find a mirror in your house and prove this for yourself. Our last topic for today is all about these curved mirrors. So down at the bottom on the left, we have this spherical mirror, this spherical shell. Imagine both the inside of the sphere and the outside are mirrored surfaces. So the inside sphere would represent a concave mirror. That's our bottom middle image. So a concave mirror is one type of a curved mirror. And then the outside of the sphere, that outer surface would form what's called a convex mirror, as shown over in the bottom right. So we have convex mirrors and concave mirrors. Here, the capital C is representing the center of that sphere. It's also referred to as the center of curvature. And our capital R would be the radius of that sphere. And one other term here, the principal axis is a line that's drawn through our center of curvature and then in through the center of that mirror. So it should hit the mirror perfectly perpendicular to it. So the law of reflection still applies even if the surface is curved. It's just that now our normal line is going to change direction depending on where the ray hits the mirror. Rays that come in from far away are essentially parallel, and we'll typically use those to find what's known as a focal point. So light rays coming in parallel to this principal axis, if they are near our principal axis, they are going to reflect back through our focal point. Here the focal point is labeled as a capital F, and we're often going to look at a measurement called the focal length, which is from the mirror to that focal point, and focal length is usually written as a lowercase f. Now, one thing with spherical mirrors, if those rays that are coming in parallel to the principal axis, if they're too far away from that principal axis, they don't actually reflect through the focal point. This is called spherical aberration, and it can produce a blurry image. If you wanted all of the parallel rays to come in and actually pass through the focal point, you'd have to use a parabolic reflector, but it's a lot more expensive and difficult to make a parabolic surface than it is to make a spherical surface. So a lot of times that just isn't done. And so as long as you're only using the region of the mirror near that principal axis, it will be okay. One last thing, you should note that the focal length is exactly half of the radius for our spherical mirrors. All right, so when we're doing spherical mirrors and we're trying to figure out where an image will be located, we do what's called ray tracing, or we draw ray diagrams. And these ray diagrams will allow us to figure out what type of image is being formed, whether it's magnified or the same size or reduced in size, whether it's inverted or not as well. So very, very common. This is often referred to as geometric optics. And we'll look at first how you would draw rays for a spherical concave mirror. So we will typically draw 3 rays. Theoretically, you'd only need 2 to figure out all of the properties of the image, but the third one is essentially just there to confirm and make sure that you've gotten the correct answer. So the first ray you would draw is parallel to our principal axis. You might just call this horizontal or flat. And then it reflects off the mirror through our focal point. The second ray, this middle diagram, you draw a ray that's through the focal point, then parallel or flat. Note that all of these rays are going to start on our object, and the objects will always be drawn as arrows that start on our principal axis, and then almost always they will point upward. So we'll draw all our rays as if they start from that tip of the arrow. So we have our first ray flat through the focal point, second ray through the focal point, then flat. Our third ray is a single straight line. It's essentially away from our center of curvature to the mirror, and then back straight through the center of curvature. So you just line up your ruler with the center of curvature and the tip of the arrow, and then draw a line along that path. So when we're drawing these rays, we don't draw 3 separate diagrams for each ray. We draw one diagram and then the next on that same diagram and then the next. So here it's the same 3 images, but now we're adding these new rays right on top. So our first ray flat through the focal point. To that we will add through the focal point, then flat. And then to that, we will add that straight away from the center of curvature and then back through the center of curvature. So note that we have these 3 rays all intersecting at a single location, and that location is where the tip of the image arrow is. So I mentioned before the object is drawn as an arrow that starts on our principal axis. Here it's position O, and the tip of our object arrow is O prime. Our image starts on the principal axis as well, here, point I, and the image arrow tip is where those lines intersect, I prime here. So with concave mirrors, there's kind of 3 possible images that can be produced. The first scenario we'll look at is when the object is located between the center of curvature and our focal point. And here, if our object is within those 2 points, then the image will be real. And a real image is an image that is formed in front of the mirror. And one way you can test if it's a real image, probably the most straightforward way, is you'd put a little screen there, a piece of paper, for example. And if you can project the image onto the piece of paper, then it's a real image. So for example, projectors in a classroom that are projecting an image onto a whiteboard or a projector screen, that's creating a real image. And we can tell because you can actually see the image, you can project it onto a surface. Our image is also inverted, it's upside down, and it's magnified. And I can tell it's magnified because the image arrow is longer than the object arrow. Next, we'll look at what happens if the object is outside of the center of curvature. So if it's farther away than the center of curvature, here, this diagram just inverted our previous diagram, where now our what was the image, that upside down arrow, is now representing the object, and what was the object is now the image. So that's kind of interesting to think about how the geometry works here. Normally, the object is drawn as an upright arrow, but oh well, just to save themselves some time, they essentially use the same image again. So we have our image now being still real, so you could put a piece of paper there and project that image onto a screen. It is inverted. Here our image is upright, but since the object itself was upside down, that means it's flipped the image. And now the one change from before is it's reduced in size. So our image arrow is smaller than the object arrow. The third scenario is when it's between our focal point and the mirror. And drawing these rays is slightly different. So first, I'll talk about how you would draw the rays, then we'll talk about these properties of the image. So the first ray is the same, flat, then through the focal point. The second ray is different. So our second ray, we used to draw from the tip of the arrow through the focal point and then flat. But here, if you imagine starting on the tip of our object arrow and going through the focal point, you're going to be drawing a line that's going away from the mirror, right? It's never going to hit the mirror. So you still line it up the same. You line up your ruler with the focal point and the tip of your arrow. But rather than drawing it from the arrow through the focal point, you just go in the opposite direction. So line up the focal point and tip of the object arrow and go toward the mirror, and it still reflects off flat. Our third arrow or ray is still the same, away from the center of curvature, then back straight through the center of curvature. But note that our three reflected rays, you can see those reflected rays over on the far left side, those arrows. Those lines are all diverging, they're spreading apart. So to find out where they will intersect, I need to use dashed lines to imagine where those lines actually originally came from, or where they would have intersected back in time. So I use these dashed lines. We always use dashed lines behind the mirror. And I can see they are meeting up where our virtual image is located. So this is now a virtual image. If you put a piece of paper behind the mirror, you are not going to project that image onto the piece of paper. It is upright, we can tell, because both the object and the image point in the same direction. And it is magnified, it's larger. So this is the only type of mirror that is going to give you an upright and larger image. This would be like cosmetic or makeup mirrors where you want to magnify some reflection. Moving on to convex mirrors. Convex mirrors, the diagrams are maybe a little tricky to draw, but the good news is that the image is always the same. So it always is upright, it's always virtual, and it's always reduced in size. So convex mirrors, the bad thing about them is they make things smaller, right? So objects are closer than they appear. You may have seen that on the side mirrors of your car. The good thing about them is that they provide a wider field of view. So they make things smaller, but they allow you to see more. So they allow you to see more into what would be the blind spots on a car. The three rays that you draw for convex mirrors are the following. So ray 1, you would draw flat and then away from the focal point. Note that ray you do continue on through the focal point. So that one is still fairly similar. Just keep in mind the one that actually goes through the focal point is imaginary, so it's dashed. Our second ray, we used to do either through the focal point or away from the focal point first, then flat. Now we're going to do toward the focal point. So it's still the same kind of scenario. You line up your ruler with the tip of the object arrow and the focal point, and you draw the line toward the mirror. Just once you hit the mirror, don't keep going. So that ray reflects off parallel. This is the bottom reflected arrow, number 2. And that one also we need to extend over behind the mirror to the right. Our third ray is still the same. Through the center of curvature. Just keep in mind that the actual light ray doesn't pass through the center of curvature, it reflects back outward. But we will continue that line with dashed line to the center of curvature, and you can see where those dashed lines all meet up. So besides ray diagrams, we can also use equations to understand what's happening with the objects and images with mirrors. So just some variables that you'll need to keep in mind. Lowercase f is the focal length that's measured from the mirror to our focal point. DO is the object distance. That distance is also measured from the mirror. DI is image distance, again measured from the mirror. And M is magnification. It tells you how large the image will be relative to the object. On the AP equation sheet, they use the letter S instead of the letter D for position or distance. And I think they use a capital M for magnification, but you should still recognize the equations. All right, so there's two main equations that we use with curved mirrors. The top one is our magnification equation, and it's equal to the ratio of the image height over the object height. So those heights are basically the sizes of the image and the sizes of the object. Because these are ratios, you can use whatever units you want. They just need to be the same units, and they will cancel out. So magnification does not carry any unit itself. It will just be a number. It's also equal to the negative ratio of the image distance over the object distance. Again, we can use whatever units we want for those distances. They just need to be the same so that they will cancel out. The bottom equation is sometimes known as the mirror equation. It also works for lenses, so later on we'll probably refer to it as the lens equation. But it's 1 over DO plus 1 over DI equals 1 over F. And both of these are on the equation sheet. All right, so sign convention, probably the most important thing when using these equations, especially because this will change when we move on to lenses. So our focal length is positive for concave mirrors and negative for convex. DO is always positive. DI is positive when the image is on the reflective side or in front of the mirror, and it's negative when behind. So for those first three, I always remember in front of the mirror is positive, behind the mirror is negative. For the bottom three, magnification is positive when the image is upright, and it's negative when the image is inverted. So keep in mind, a negative magnification doesn't necessarily mean smaller, it just means upside down. Our object height will always be positive, and image height will be positive if it's upright, and it will be negative if it's inverted. I think the heights kind of are pretty logical. All right, here we have our last slide for today. Go ahead and pause and resume when you're ready. So first, for the type of mirror, there's only one mirror that can magnify your face, especially if you want it to appear upright at least, and it has to be a concave mirror. And we should already know it has to be where your face is in between the focal point and the mirror itself. For part B, the type of image, we know with a concave mirror, when the object is between the focal point and the mirror itself, that the image is upright and virtual. It's also magnified, but we already knew that. And for C, the radius of curvature. Radius of curvature does not appear in any of our equations, but first I'm going to use magnification to solve for the image distance. So 1.33 was given as the magnification factor. I know the object, your face, is 20 centimeters in front, and I can get DI as negative 26.6. So that's another sort of check that the image is virtual. Since image distance is negative, that means behind the mirror, and that means virtual image. I can then use DI in my mirror equation to solve for the focal length. So I'm just plugging in DI and DO. I get a focal length of 80.6 centimeters, and now there is a relationship between radius of curvature and focal point, and that's just that the center of curvature was double our focal point. So multiply that by 2, and I get my radius of curvature.